Imagine spending $500,000 on a Ferrari, taking it to the track, and watching your temperature gauge climb into the red zone after just 3 hot laps. Meanwhile, a Chevrolet Corvette that costs 1/5 the price keeps hammering away lap after lap, its temperature needle barely moving. Sound impossible? That's exactly what started happening at racetracks across America in 2014, and the engineering story behind it involves a $47 part that changed everything. And picture this. It's a blazing hot day at Virginia International Raceway. The asphalt is literally soft enough to leave footprints. A Ferrari 458 Italia worth $450,000 pulls into the pits, its engine management system having cut power to prevent catastrophic overheating. The owner watches in disbelief as a Corvette Stingray, a car that costs less than his Ferrari's optional carbon fiber package, continues circulating at full speed. The Corvette's driver isn't babying it either. He's pushing hard, brake zones glowing, tires squealing, engine screaming to redline, lap after lap after lap. The Ferrari owner asks his mechanic what's wrong with his car. Nothing, the mechanic says. It's working exactly as designed. This is the story of how Chevrolet engineers solved one of the most persistent problems in high-performance driving, heat management, using an approach so elegantly simple that European manufacturers initially dismissed it as crude American thinking. They stopped laughing when Corvettes started embarrassing supercars worth 5 times as much at track days around the world. The solution wasn't exotic materials or complex electronics. It was understanding the physics of heat transfer and applying that knowledge with obsessive attention to detail. To understand why this matters, we need to travel back to 2005. General Motors was developing the 6th-generation Corvette, the C6. The automotive world was changing. Track days were becoming popular among wealthy enthusiasts. Cars weren't just being driven to dinner anymore. They were being flogged around road courses by amateur drivers pretending to be racing heroes, and there was a problem that nobody wanted to talk about publicly. Most high-performance street cars, especially the expensive European ones, couldn't handle sustained track use without overheating. Ferrari, Lamborghini, McLaren. They all had the same dirty secret. Their cars were designed to achieve spectacular performance numbers in short bursts. 0 to 60 in 3 seconds. Quarter mile in 11 seconds. Top speed of 200 miles per hour. But ask them to maintain that performance for 20 minutes on a racetrack? Different story. The engines would get too hot, oil temperatures would soar, coolant would boil. Electronic nannies would intervene, cutting power to save the engine from destroying itself. Owners who'd spent supercar money found themselves being passed by modified Honda Civics because their $500,000 toys had gone into limp mode. Once the exotic manufacturers had their reasons, their customers, they reasoned, bought these cars for image and occasional thrills, not genuine track use. Racing versions existed for people who wanted to actually race. Street cars needed to be quiet, comfortable, and emissions compliant. Track-capable cooling systems were bulky, noisy, and expensive. Why add weight and complexity for something 99% of owners would never need? Besides, if someone could afford a Ferrari, they could afford a dedicated track car, too. And Chevrolet saw opportunity in this compromise. The Corvette had always been the blue-collar supercar, the working man's exotic. Its buyers weren't collecting them like art pieces, they were driving them, hard. And increasingly, they were taking them to track days where they had to share the asphalt with Porsches and Ferraris. If Corvette could solve the cooling problem without breaking the bank, they'd have a genuine advantage over cars costing several times as much. The engineering team, led by Taj Jukter, Corvette's chief engineer since 2006, started by studying exactly what happened during track driving. They instrumented test cars with dozens of temperature sensors: oil temperature, coolant temperature, intake air temperature, transmission fluid temperature, differential temperature, even brake fluid temperature. They ran these cars for hours at racetracks in Arizona summer heat, Death Valley, and the Nürburgring. They discovered something interesting. The problem wasn't just engine cooling, it was system-wide heat management. Everything in a performance car generates heat under track conditions. The engine is obvious. Internal combustion is literally controlled explosion, but the transmission generates massive heat from friction as gears mesh under load. The differential heats up as it transfers power to the wheels. Brakes convert kinetic energy to heat, lots of it. Even the power steering system generates heat as it works overtime, helping the driver wrestle the car through corners. All this heat has to go somewhere. In most cars, it accumulates until something overheats. Here's where Chevrolet's approach diverged from the Europeans. Instead of treating each heat source independently, they looked at thermal management as an integrated system. The breakthrough came when they realized they didn't need exotic solutions. They needed better implementation of existing technology. The magic was in the details. Let's talk about the LT1 engine that debuted in the 2014 C7 Corvette. At first glance, it seems conventional. A 6.2-liter pushrod V8. Old technology, the Europeans scoffed. Pushrods? How primitive. Ferrari was using dual overhead cams and variable valve timing. McLaren had turbos. Lamborghini had already moved to dual-clutch transmissions. But those European critics missed something crucial. The LT1 wasn't just any pushrod V8. It was a pushrod V8 designed from the ground up for sustained high-performance use. The cooling system was the cornerstone of this philosophy. Start with the basics. Coolant capacity. The LT1's cooling system held 11.5 quarts of coolant. That's more than many trucks. More coolant means more thermal mass, more ability to absorb heat before temperatures rise. But capacity alone wasn't enough. Next, the water pump was a revelation. Traditional water pumps are driven by the engine, meaning they pump proportionally to engine speed. Problem is, cooling needs don't scale linearly with RPM. At idle in traffic, you need significant flow to prevent heat soak. At high RPM on track, you need massive flow to handle the heat generation. Chevrolet's solution? An electronically controlled variable flow water pump. It could adjust flow rate independently of engine speed, delivering exactly the cooling needed at any moment. The pump could flow up to 150 gallons per minute at maximum. That's 2.5 gallons per second coursing through the engine. For perspective, that's enough to empty a standard bathtub in 20 seconds. But flow rate was only part of the equation. The path that coolant took through the engine was equally important. Austin Chevrolet engineers redesigned the coolant passages using computational fluid dynamics. Every passage was optimized for maximum heat transfer with minimum restriction. They paid particular attention to the cylinder heads, where combustion heat is most intense. The passages around the exhaust valves were enlarged. Why? Exhaust valves run hotter than intake valves. They're exposed to 1,500-degree exhaust gases. Traditional designs often struggle to cool these areas adequately, leading to localized hotspots that can cause detonation or valve failure. And the LT1 also featured targeted cooling jets. These are small nozzles that spray coolant directly onto the underside of each piston. Pistons take enormous heat from combustion. The crown can reach 600 degrees Fahrenheit. The oil jets keep them cool, preventing expansion that could cause seizure. But here's the clever part. The jets only activated above 4,000 RPM or under high load conditions. Why not all the time? Because cold pistons increase friction and emissions. The system was smart enough to know when cooling was needed and when it wasn't. And then now, let's talk about that $47 part that changed everything. Oil coolers. Every high-performance car has one, right? Not exactly. Many have oil coolers, but they're often undersized afterthoughts, added to meet minimum requirements rather than provide genuine track capability. The C7 Corvette's oil cooler was different, and first, it was huge. The heat exchanger core was nearly a foot square and 2 inches thick. That's more cooling surface than many dedicated race cars. But size wasn't the innovation. Location was. Chevrolet engineers positioned the oil cooler in the front corner of the car directly in the airstream. No sharing airflow with the radiator or intercooler. Its own dedicated supply of cool air. But here's where it gets really clever. The oil cooler wasn't just connected with hoses like most cars. Chevrolet designed a thermostatic valve system that monitored oil temperature constantly. When oil was cold, the valve bypassed the cooler entirely, allowing oil to warm up quickly for proper lubrication. As temperature rose, the valve gradually opened, sending more oil through the cooler. At full temperature, 100% of oil flow went through the cooler. This prevented overcooling while ensuring maximum cooling when needed. The system maintained oil temperature between 220 and 250 degrees Fahrenheit, regardless of conditions. That's the sweet spot for oil performance. Hot enough for minimum viscosity and maximum lubrication, cool enough to prevent breakdown. European competitors often saw oil temperatures exceed 300 degrees on track, forcing reduced engine power to prevent damage. But Chevrolet didn't stop at engine cooling. The transmission needed attention too. The 7-speed manual transmission in track-focused Corvettes featured its own cooling system. A pump circulated transmission fluid through a dedicated cooler mounted in the front bumper. Why does a manual transmission need cooling? Under track conditions, the synchronizers and gear faces generate tremendous heat from repeated high RPM shifts. Without cooling, the transmission fluid breaks down, leading to notchy shifting and eventual failure. The automatic transmission got even more attention. The 8-speed automatic featured a transmission fluid cooler with nearly double the capacity of competitors. The fluid pump was electronically controlled, varying flow based on temperature and load. During casual driving, minimal flow reduced parasitic losses. During track driving, maximum flow kept temperatures in check, and the differential received similar treatment. The electronic limited slip differential in the Z51 performance package included a dedicated cooling pump and heat exchanger. Under normal driving, the pump remained off. But when sensors detected high differential temperatures from repeated corner exits on track or burnouts, not that Corvette owners would ever do burnouts, the pump activated, circulating fluid through the cooler. And even the brakes got the thermal management treatment. The Corvette's brake cooling system wasn't just hopes and prayers like many street cars. Engineers designed specific ducting to channel air directly to the brake rotors and calipers. The ducts featured carefully calculated inlet sizes and angles to maximize airflow without increasing drag. The brake rotors themselves were directionally vanned, meaning the internal cooling vanes were curved to pump air through the rotor like a centrifugal fan. Here's where Chevrolet's integrated approach really shined. All these cooling systems were connected through the car's computer network. The engine control module talked to the transmission control module, which talked to the differential controller, which monitored brake temperatures. If any system detected excessive heat, it could request increased cooling from other systems. For example, if brake temperatures spiked, the system could increase engine cooling fan speed to improve overall airflow through the car. The computer system also featured something called Performance Algorithm Liftfoot. I know, terrible name, but brilliant function. During track driving, when the driver lifted off the throttle entering a corner, the system would automatically increase cooling pump speeds and fan speeds. Why? Because that's when the car had a moment to catch its breath, so to speak. Maximum cooling during minimum load periods helped maintain temperatures during the next high-load section, and Chen testing proved the system worked. Chevrolet engineers ran a C7 Corvette Z06, the supercharged 650 horsepower monster, for 24 continuous hours at Virginia International Raceway. Professional drivers rotated through, running flat out the entire time. The only stops were for fuel and tires. After 24 hours of absolute abuse in summer heat, the car showed no signs of overheating or reduced performance. Try that in a Ferrari 488 and real-world results backed up the testing. At track days across the country, a pattern emerged. Corvette owners were running full sessions without temperature issues, while owners of European exotics were constantly monitoring gauges and backing off to cool down. Car and Driver magazine did a comparison test at lightning lap. A C7 Corvette Grand Sport lapped faster than a McLaren 570S that cost twice as much. The McLaren was faster on individual laps, but it couldn't maintain the pace. After 3 hard laps, it went into thermal protection mode, reducing power. The Corvette? It ran consistent lap times all day long. The financial implications were staggering. A track-prepped Corvette with the Z51 performance package cost around $70,000 in 2014. That included the enhanced cooling system, electronic limited-slip differential, upgraded brakes, and magnetic ride suspension. A comparably capable Ferrari 458 Italia started at $240,000, and that was before options. Add the racing-derived cooling upgrades to make it truly track-capable? You're looking at $300,000 minimum, but here's the kicker. Even with those upgrades, the Ferrari still struggled with sustained track use. Ferrari's solution was the 458 Speciale, a track-focused version with enhanced cooling, stripped interior, and aerodynamic improvements. Price? $290,000 base, easily reaching $350,000 with options. And it was still more finicky than the Corvette, requiring specific warm-up and cool-down procedures to prevent damage. And then the European manufacturers eventually responded. Porsche upgraded the cooling system in the 911 GT3. McLaren added transmission coolers to the 570S. Ferrari improved thermal management in the 488 that replaced the 458. But they did it grudgingly, adding complexity and cost to cars that were already expensive and complex. Meanwhile, Chevrolet had solved the problem with good engineering and a $47 oil cooler. Let me explain exactly why that oil cooler was so important. Oil does more than lubricate in a high-performance engine. It's a critical part of the cooling system. Oil sprays onto the bottom of pistons, absorbing heat. It flows through bearing surfaces, carrying heat away from friction points. In the valve train, it cools valve springs that can reach 400 degrees. If oil gets too hot, it loses viscosity. Thin oil can't maintain the protective film between moving parts. Metal touches metal. Bearing clearances increase. Ring seal deteriorates. Power drops. Eventually, something fails catastrophically. And most manufacturers spec their high-performance engines for 5W30 or EW40 oil. These oils maintain adequate viscosity up to about 250 degrees Fahrenheit. Above that, they start breaking down. The Corvette's cooling system kept oil temperature below 240 degrees even during extended track sessions. Competitors regularly saw 280 to 300 degrees, forcing them to use expensive racing oils that could handle higher temperatures. Even then, oil changes were needed after every track day. And then the Corvette could use regular Mobil 1 synthetic and run multiple track days on the same oil. Testing showed oil analysis results after 5 track days in a Corvette were better than 1 track day in many competitors. That's hundreds of dollars saved on oil changes alone, not to mention reduced engine wear. The differential cooling system was equally innovative. Most manufacturers ignore differential cooling in street cars. After all, how often does a differential overheat in normal driving? Never. But on track, the differential is constantly working, transferring power through corners, managing wheel speed differences, engaging and disengaging clutch packs in limited slip units. All that friction generates heat. Lots of heat without cooling. Differential fluid can exceed 300 degrees. The fluid breaks down, losing its ability to lubricate. Clutch packs glaze over, losing grip. The differential starts slipping, unable to transfer power effectively. In extreme cases, the differential can weld itself solid, locking both wheels together. That's exciting when it happens mid-corner at triple-digit speeds. Hornet and Chevrolet's differential cooler maintained fluid temperature below 200 degrees. The fluid lasted longer, the clutch packs maintained consistent grip, and the differential performed predictably lap after lap. It was another example of solving a problem that competitors pretended didn't exist. And the brake cooling deserves special attention too. Brake fade. The loss of braking power due to overheating is terrifying. You arrive at a braking zone at 150 miles per hour, hit the pedal, and nothing happens. The pedal goes to the floor, your life flashes before your eyes. If you're lucky, there's runoff area. If not, well, hope your insurance is paid up. An engine brake fade happens when the pads and rotors get so hot that the pad material literally vaporizes at the interface. This creates a gas layer between pad and rotor, preventing contact. No contact, no friction. No friction, no stopping. The only solution is cooling. Get air to the brakes to carry away heat. Chevrolet's brake cooling system used multiple strategies. First, those ducted inlets we mentioned, but also the wheel design itself was optimized for brake cooling. The spokes were shaped to pump air outward as the wheel rotated, drawing cool air through the brake assembly. The brake shields were designed with specific gaps to channel airflow. Even the underbody panels were shaped to create low-pressure zones that pulled hot air away from the brakes. And during testing at Road Atlanta, a notoriously brake-intensive track, Corvette engineers measured brake temperatures during a 20-minute session. Maximum temperature reached 1,100 degrees Fahrenheit, well within the 2,300-degree limit of the brake pads. A Ferrari 458 at the same track regularly exceeded 1,400 degrees, triggering brake fade warnings. The magnetic ride suspension played a surprising role in thermal management too. By constantly adjusting damping rates to maintain optimal tire contact, it prevented excessive tire slip. Slip generates heat. Hot tires lose grip, causing more slip, generating more heat. It's a vicious cycle. The Corvette suspension kept tires in their optimal temperature window, maintaining grip and preventing overheating. And this systematic approach to thermal management had interesting secondary benefits. Because nothing was overheating, nothing was operating at the edge of failure. Reliability improved dramatically. Warranty claims dropped. Corvettes that were tracked regularly showed similar wear patterns to those driven conservatively. Try tracking a Ferrari regularly and watch your warranty evaporate faster than brake fluid at lagunaseca.tn, the racing world noticed. IMSA, the sanctioning body for sports car racing in North America, had to repeatedly adjust their balance of performance rules because privateer Corvette teams were embarrassing factory Ferrari and Porsche teams. The Corvettes could run longer stints without overheating, maintain consistent lap times, and required less maintenance between races. What started as street car development had created a legitimate racing advantage. But perhaps the most impressive validation came from an unexpected source. In 2016, a group of Ferrari engineers visited the Bowling Green assembly plant where Corvettes are built. Officially, they were studying American manufacturing techniques. Unofficially, according to plant workers, they spent hours examining the C7's cooling system, taking photographs and measurements. Imitation is the sincerest form of flattery. And the C8 Corvette, which moved to a mid-engine layout in 2020, took thermal management even further. With the engine behind the driver, cooling became even more critical. Chevrolet responded with five heat exchangers, 2 radiators, an oil cooler, a transmission cooler, and a differential cooler. The system could reject over 100 kilowatts of heat, enough to heat a small house in winter. The C8's party piece was active aerodynamics tied to the cooling system. When temperatures rose, the front splitter automatically adjusted to increase airflow to the radiators. The rear spoiler changed angle to reduce drag, allowing more air through the engine bay. Body panels contained hidden vents that opened when cooling demand increased. It was like the car was breathing, adapting its shape to maintain temperature. Testing at the Nürburgring, the C8 Z06 ran the full 12.9-mile Nordschleife lap in 7 minutes and 10 seconds. More importantly, it could do it repeatedly without overheating. A Lamborghini Huracan Performante that ran a similar time required a cool-down lap between hot laps. The Ferrari 488 Pista needed careful temperature management to prevent limp mode. The Corvette just kept going. So what was Chevrolet's secret? It wasn't a secret at all. It was engineering discipline. While competitors chased headline numbers, maximum horsepower, lowest weight, highest top speed, Chevrolet focused on sustained performance. They asked different questions. Not us, how fast can it go? But us, how fast can it go for an hour? Not us, how much power can it make? But us, how much power can it make repeatedly? This philosophy extended to every component. The supercharger in the Z06 had its own intercooler system with a dedicated electric pump. Why electric? Because it could run after the engine shut off, preventing heat soak. The fuel system included a cooler to prevent vapor lock from hot fuel. Even the engine oil pan was designed with specific baffles to maintain oil pressure during high G corners while providing maximum surface area for heat dissipation. The attention to detail was obsessive. Chevrolet engineers discovered that traditional hood vents could allow hot air to recirculate at certain speeds. They developed vents with one-way valves. Air could exit, but not enter. They found that painting the underside of the hood white instead of black reduced radiant heat transfer to the intake manifold by 12 degrees. 12 degrees might not sound like much, but in a turbocharged engine, that's the difference between consistent power and heat-induced knock retard. The transmission cooling in the dual-clutch automatic was particularly clever. The system used engine coolant to warm the transmission fluid during cold starts. Warm fluid shifts better. Then switched to dedicated cooling once operating temperature was reached. The computer predicted cooling needs based on driving style. Aggressive shifts and launches triggered preemptive cooling increases. And even the air conditioning system was part of the thermal management strategy. During track driving, the AC compressor could be automatically cycled off during full throttle acceleration to reduce engine load, then reactivated during braking and cornering. This maintained cabin comfort without sacrificing performance. The system was so effective that drivers could run full track sessions with the AC on in 100-degree weather. Then the European response to Corvette's cooling advantage was predictable. First, denial. Surely these American cars couldn't really maintain performance better than European exotics. Then dismissal. Cooling systems are for people who can't afford multiple cars. Then grudging acceptance. Okay, maybe sustained performance matters. Finally, adoption. The latest Ferrari SF90 has 7 cooling circuits. But here's what the Europeans still don't seem to understand. It's not about the number of coolers or the complexity of the system. It's about integration and optimization. The Corvette's cooling system works because every component was designed to work together from the beginning. It wasn't added on to fix problems discovered during testing. It was fundamental to the design. The cost difference remains staggering. A 2024 Corvette Z06 with the Z07 performance package, essentially a street-legal race car, starts at around $120,000. It includes carbon ceramic brakes, Michelin Pilot Sport Cup 2R tires, and the most aggressive cooling package Chevrolet offers. A similarly track-capable Ferrari 296 GTB? Try $350,000 minimum, a McLaren 765 LT, $400,000, a Lamborghini Huracan STO, $330,000. Nanons know all those cars are engineering marvels. They're faster than the Corvette in short bursts. They have more advanced materials, more complex electronics, more prestigious badges. But take them to a track day in August in Texas and watch which car is still running at full power after an hour. The answer might hurt some European egos. The real genius of Chevrolet's approach wasn't in any single innovation. It was in recognizing that sustained performance is more valuable than peak performance for actual driving enjoyment. It was in understanding that reliability and consistency matter more than bragging rights. It was in solving problems thoroughly rather than just adequately. This philosophy represents something fundamentally American about engineering. It's not about showing off with complexity. It's about getting the job done effectively. The pushrod V8 that Europeans mock as primitive, it's compact, lightweight, reliable, and torquey. The leaf spring suspension they called outdated, it's light, simple, and works brilliantly. The cooling system they initially ignored, it embarrasses cars costing 5 times as much. Nennis, there's a larger lesson here about innovation. Sometimes the best solution isn't the most exotic or expensive. Sometimes it's taking existing technology and implementing it correctly. Chevrolet didn't invent oil coolers or water pumps or cooling ducts. They just used them better than anyone else. They paid attention to details others ignored. They solved problems others pretended didn't exist. And the track day hero who started our story, the Corvette owner lapping while the Ferrari overheated, he's not unusual. Visit any track day in America and you'll see the same pattern. Corvettes running session after session while European exotics take extended breaks to cool down. It's not because Corvette owners are better drivers or more dedicated. It's because their cars were engineered for this reality from the start. The development of Corvette's cooling system also reveals something important about American manufacturing capability. While we often hear that American industry can't compete with German precision or Italian passion, the Corvette proves otherwise. It shows that American engineers can solve complex problems with elegant solutions. They can build world-class performance cars that actually work in the real world, not just on magazine covers. Looking forward, thermal management will become even more critical. As engines become more powerful and more efficient, they generate more heat in smaller packages. Electric vehicles face even greater cooling challenges. Batteries and motors generate enormous heat under performance driving. The lessons Chevrolet learned solving Corvette's cooling challenges are already being applied to the electric future. In NHN, the Corvette cooling story is ultimately about respect. Respect for the customer who's going to actually drive the car hard. Respect for the engineering challenge of sustained performance. Respect for the physics that govern heat transfer. And, perhaps most importantly, respect for the idea that a performance car should perform whenever the driver demands, not just when conditions are perfect. Nenchen. So the next time you see a Corvette at a track day running lap after lap while more expensive machinery sits cooling in the paddock, remember this story. Remember that somewhere in Detroit, a team of engineers decided that ordinary Americans deserved supercar performance that actually worked. They decided that a $47 oil cooler and some careful thinking could embarrass cars costing hundreds of thousands more. They decided that solving problems properly mattered more than impressive spec sheets. Nansen, that's the beauty of American engineering at its best. It's not about prestige or tradition or doing things the way they've always been done. It's about looking at a problem, understanding it completely, and solving it effectively, even if that solution seems too simple to the Europeans, especially if it seems too simple. The Corvette's cooling system isn't just a technical achievement, it's a philosophical statement. It says performance isn't just about going fast. It's about going fast repeatedly, reliably, consistently. It says that engineering excellence isn't measured in complexity, but in effectiveness. It says that sometimes the best solution is the one that just works. Dan Chen, what's the most impressive feat of engineering problem-solving you've witnessed? Let me know in the comments below. If you enjoyed this deep dive into how Detroit outsmarted Maranello with clever engineering and a $47 part, make sure to subscribe for more stories of American innovation embarrassing the establishment. Until next time, keep those engines cool and those lap times consistent.